All right, class. So this video is about the process of finding the single value decomposition of a matrix. And before we dive in, just a little bit about the idea behind this. Remember from the last section that things were really nice if A was symmetric, because then we could find orthonormal bases Q, so that we could write A as QD Q transpose. Okay, that was really nice, where this is a diagonal matrix with the eigenvalues on the diagonal. Okay, and Q is an orthogonal matrix. Really nice, about as nice as you can get. Someone had the genius idea, since, remember, this you can only do if it's symmetric. So someone had the idea, well, what if we had a non-symmetric matrix? Any m by n matrix. And then created a symmetric matrix by multiplying by its transpose, because this is always symmetric. And then we kind of did a similar analysis on this matrix. This is technically a covariation matrix. So do a covariation, an analysis on the covariation matrix of A, and maybe we could get some leverage by doing that. And it turns out you get great leverage. So you could start off by writing A transpose A equals Q D Q transpose. And you do the math, and you have to do some figuring out to keep sizes working out all right and stuff, but eventually you can get down to A equals U sigma V transpose. But things are a little bit different. This is no longer square. It's the size of A. And it's a sorted diagonal matrix, but it has the square roots of the lambda i's on the diagonal. And lambda I, so the lambda I is are the eigenvalues. Gosh, this is not the best. Of A transpose A. And this is an orthogonal n by n, m by n, that is U is, and V is an orthogonal n by n matrix. And so it's similar kind of structure. You have to give up something. Q isn't, you don't just have Q and Q transpose. The sizes are a little bit crazy, but it turns out to be extremely, extremely valuable. So the whole idea was, hey, maybe we can get some leverage by analyzing A transpose A, which is symmetric, and use our knowledge about symmetric matrices. And we can do that, and you get this structure, which is called the singular value decomposition. And the square roots of the eigenvalues of A transpose A, we call them sigma i's, they are called the singular values of A. Really messed this up. So one of the big mistakes is people starts to find the eigenvalues of A and then take the square roots of those. No, you have to write A transpose A, and then do that, and then you end up taking the square root. So this is the process of, like, if we were given an A, how do we go about finding all that stuff? So first, we're going to find the eigenvalues of A transpose A. So we're going to take A, find the transpose, multiply that out. We're going to get a symmetric matrix, and it's going to be square, and so we can find eigenvalues. And we'll find the orthonormal basis of the eigenvectors for that. And that's going to be how we build our B. Okay? Sigma is the m by n diagonal matrix with entries as the singular values in decreasing order. And the key thing is that sigma and A are the same size. Okay, so that makes it pretty easy. Same size. Then we can take all of our VI's that we found in the eigenvectors and unitize them, make them of unit length, and put them together, and that makes VI. That makes V. And we'll order them in the same order, whichever way they match up with the singular values that we put in sigma. So to make U, we take A, multiply it by VI, and divide by the singular value, and that gets us the ith column of U. So if we want the first column, we take of U, we take the first column of V, multiply it by A, divide by the singular value, and we'll get UI. And then we might not have enough to build U, and if so, we need to build an orthonormal basis. So we might have to add some vectors and then do Gram-Schmidt to orthogonalize them and then normalize them to finish off U, and then we can just write U with all of that orthonormal basis, with columns as that orthonormal basis. Okay, so let's do an example. So here's a simple matrix. We want the single value decomposition. The first thing we need to do is find A transpose A. So we multiply that out. And on some previous slides that I haven't talked through yet, they already go through and find the eigenvalues of this. You already know how to do that. So hopefully you do. 3, 1, and 0. But that means that the singular values are the square root of 3 and the square root of 1, which is 1. So square root of 3 and 1, they are the singular values, not 3 and 1. So so now we can use those to build sigma. We take a matrix of zeros that's the same size of A, and then down the diagonal we write down the singular values in descending order. This is a mistake. I'm sure they were supposed to write A there. It's the same shape and size as A, and in descending order. Technically, you could do it another way. This is just a convention, but for uses when you apply this in problems, the larger the columns of U and V that correspond to the larger singular values turn out to be much more important and tell you a lot more about what's happening in the situation, or have most of the information. So we just put those first. So we need to start constructing the V matrix. So once again, we're doing A equals U sigma V transpose. And the columns here, they are the eigenvectors of A transpose A. So we subtract off our eigenvalues, look at the basis for the null space. So that's what we do. We subtract off 3i from A transpose A, and then do the process we've done a bazillion times by now this semester. Find the solution for that equals 0, or the basis for the null space, and we end up with a single vector. So we've normalized this so it has length 1. So 2, 1, 1 is a basis for the null space, but we want an orthonormal basis, so you divide by the length. And then doing 1, get a similar thing, go through, we find this, have to divide by the length, so we end up with this one. And 0, if we subtract 0, Then from the diagonal, we just have the matrix itself. We row reduce and find the null space, and we get this vector, but we have to divide by its length, so we get this one. So now we have 3 vectors. They correspond to the 3 eigenvalues, the 3 singular values. They're in descending order. So so square root of 3 is larger than 1, which is larger than 0. So now we can just write those together to make our v. So that's what we've done here. So this corresponds to the singular value of the square root of 3. This is the 1. This is 0. So, okay, so now we have v. Now we can use v to find u. So you can find the first column of u by taking the first column of v, multiplying it by a, and dividing by the singular value that corresponds to the first column of v, which is the first one. So our largest singular value was the square root of 1. I'm sorry. It was sigma 1. It's the square root of 3. So we divide by the square root of 3. This is a, and this is v1. Do the multiplication, we end up with a 2 by 1. Divide by the square root of 3, we end up with this. And we do the process again with v2. Do the multiplication, end up with this. So here is u. So we were lucky we didn't have to add any to increase it to make the right size, any other vectors. So we're nice. So now we found u, we found sigma. Here's u, here's sigma, here's v, and if we do all of that multiplication, we will end up with this. So, and it looks a lot more complicated, but if you watch the other video, you'll understand what this gives us. We did it in the context of a picture, but you can also do it in terms of other things. So these columns tell you things about the matrix, things that are, when you've got a very large data set, it might be much harder to figure out. So let's do another example. So here we have a 3 by 2. To start off, we create a symmetric matrix of A transpose A. We end up with this 2 by 2 matrix. This is nice. We see that the eigenvalues are both 4 because it's a diagonal matrix. Subtract off 4, both x1 and y1 are free, and so 1, 0, and 0, 1 are perfect, or great basis vectors. So we can make v1, 1, 0, v2, 0, 1. And see this note. These are already orthonormal. We don't have to normalize. Because we already know that since this is a symmetric matrix, we will have orthogonal eigenvectors as long as we have independent, like unequal eigenvalues for each for each different eigenvalue. But if you have an eigenvalue with multiple, that has a multiple algebraic multiplicity, then it's not guaranteed, and you might have to do Gram-Schmidt to orthogonalize those. Okay, so now we can write down sigma and v. So we take sigma is the same size as A. A was a 3 by 2, so we write down a 3 by 2, and we divide by we take the eigenvalues, take the square roots, which are our singular values, write those down the diagonal, so we just get 2, 0, 0, 2, 0, 0. And v they're already normalized and orthogonalized vectors, eigenvectors of A transpose A. Now to find the columns of u, we can take v1 here, multiply A times v1, and divide by the singular value, largest singular value, and we end up with, we get this one. We do that again with the second one. So here's A, here's the singular value, we divide, we get another one. Great. But we have a problem because U needs to be 3 by 3. We need to be able to, it needs to be a square matrix that we can multiply by sigma. And so, and sigma is 3 by 2. So that means that here we need a square matrix, V, so that needs to be 2 by 2. We multiply by V transpose, but it's square, so that's the size of V transpose 2. Here we need a 3 by 3 because we want a square matrix so we can multiply by 3 by 2, and we only end up with two matrices, or sorry, two vectors, two basis vectors. So we need another one, and there's a couple different ways to do this. We can pick a vector, maybe 0, 0, maybe 0, 0, 1, or 1, 0, 0, or something, 1, 1, 1. And then we can do Gram-Schmidt and subtract the projections of these two off of that one. Or, since we only need one more, we can pick any x, y, z and dot product with each of those, and we want both of them to be 0. That's what we'll do here. And then we get a system of equations. So we take the dot product, gives us one system, that one equation that has to be 0. Take the dot product with the second one. That one has to be 0. And then we can row reduce, find the null space, and we end up with this one, but it's not normalized, so we normalize it, and then so we add that on. So so now we have our 3 vectors, an orthonormal basis. So U is an orthogonal matrix, and now we should be able to check that this U times this sigma times that V transpose is actually A. So great. Next video we'll talk about more in detail about a little more of the theory and a little bit of another way to make sense of what's going on with these. Okay, thanks.